Welcome to The Explainer. Today, we're cracking the code of one of chemistry's greatest inventions, the periodic table. You know, it's so much more than just a chart on the wall. It's basically a map to the building blocks of our entire universe.
So just think about this for a second. How do you possibly bring order to that much chaos? Imagine trying to organize a massive library but with no catalog system whatsoever. That's the exact challenge early chemists were up against. Let's dig into how they created the ultimate filing system for the elements.
Okay, so our story really kicks off in the early 1800s with a chemist named Johann Dobereiner. He was one of the very first people to spot a kind of hidden pattern among the elements, a little clue that maybe, just maybe, they weren't just a random collection of stuff.
He figured out that you could group some elements into these little families of three, or triads, that all had similar chemical properties. But here's the really clever part, the math behind it. He realized the atomic weight of the middle element was almost a perfect average of the other two.
Just take a look at this example with lithium, sodium, and potassium. If you average the atomic weights of lithium and potassium, you get 23, which is the exact atomic weight of sodium. I mean, that's pretty cool, right? It was a groundbreaking idea, but it was just a starting point. This triad system, well, it only worked for a few elements.
So next up, we have a chemist with a bit of a musical side, John Newlands. Back in 1865, he came up with the law of octaves. He suggested that when you line up the elements by atomic weight, their properties repeat every eighth element, just like musical notes in a scale. It was a really creative idea, but it didn't quite work for all the elements, and honestly, the scientific community kind of made fun of him for it at the time.
And then came the real game changer, the master architect himself, Dmitry Mendeleev. He created a system so powerful, it didn't just organize the elements they already knew about, it could actually predict the future.
So this was Mendeleev's big idea. He arranged all the elements by their atomic weight. But here's where his absolute genius kicks in. He wasn't afraid to leave empty spaces in his table. He trusted his pattern so much that he basically said, hey, there are elements missing here, and I bet they'll be discovered one day.
Okay, this is just mind-blowing. Look at this. He predicted the properties of an undiscovered element he called Eka aluminum. Years later, when gallium was discovered, his predictions were unbelievably accurate. I mean, right down to its density and its low melting point. He even famously said it would melt in the palm of your hand.
Now, Mendeleev's table was a masterpiece, but it wasn't quite perfect. There were a few elements that seemed to be in the wrong place if you went strictly by weight. The final crucial piece of the puzzle came from a young physicist named Henry Moseley, who found the true key to organizing everything.
Moseley discovered that the single most important property of an element isn't its weight, but its atomic number, which is just the number of protons in its nucleus. By reordering the table based on atomic number instead of atomic weight, every single element fell perfectly into place. And just like that, we got the modern periodic table we all know and love today, with its periods, groups, and blocks all sorted out.
So, now that we have this perfect modern table, let's unlock its secrets. Its real power is in the predictable patterns or trends that you can see. Understanding these is absolutely key for your exams, so let's dive into two of the most important ones.
First up, let's talk about size. As you move across a row or down a column on the table, do atoms get bigger or smaller? Well, that's what we call the atomic radius. Now, this might feel a little backwards, but as you move from left to right across a period, atoms actually get smaller. Why? Well, you're adding more and more protons to the nucleus, and that stronger positive charge pulls the electrons in tighter, shrinking the whole atom. But as you move down a group, the atoms get bigger because you're adding whole new layers or shells of electrons. Next up, ionization energy. The easiest way to think about this is like an atom's grip strength. It's how much energy it takes to pull away its outermost electron. Some atoms have a really loose grip, while others hold on for dear life.
And this chart for period 3 shows the trend perfectly. As you move from left to right, the ionization energy goes up, up, up. And this makes total sense, right? We just said smaller atoms have a stronger pull from the nucleus, which makes it way harder to snatch an electron away. That's why it's so much easier to take an electron from sodium than it is from argon.
All right, here's a super simple memory trick for your exams. Just remember this. As you move across a period, everything gets smaller and tighter. As you move down a group, everything gets bigger and looser. A tighter grip means higher ionization energy. A looser grip means it's lower. Simple as that.
Okay, so theory is great, but let's put all this knowledge into practice. We're going to walk through a typical exam question to see how it all comes together.
Let's say your exam gives you this. An element has an atomic number of 17. What can we tell about it? Okay, step 1. Its electron configuration is 2, 8, 7. Right away, that tells us it has 3 shells, so it's in period 3. The outer shell has 7 electrons, so it's in group 17. And what do we call group 17? Those are the halogens. It needs just 1 more electron to have a full outer shell, so its valency is 1. And since it wants to gain an electron, it's a nonmetal. The element is chlorine. See? Easy.
So let's do a quick recap of the really big ideas. The story of the periodic table is all about this journey from complete chaos to beautiful order. We had those early hints from people like Dobereiner and Newlands, then Mendeleev's predictive masterpiece, and finally, the modern table based on atomic number. And today, this one chart lets us predict exactly how an element will behave just by knowing its address.
All right, ready to test yourself? Go ahead and pause here and see if you can tackle these 10 questions. It's the best way to make sure you've really got it down. Thanks for joining us on this tour of the amazing periodic table.